Okay, so we're talking about some applications of exponential growth and decay, in particular continuous exponential growth and decay. And this is a little bit different than the other exponential equations that we did before. So the equations we did before would give you a percent of growth or something, like the population is growing by 3% per year or something like that. And you would take like the initial value or the starting population or whatever, call it A, and then you would add that 3% to 1, so you get something like 1.03 to the power of x or time or whatever. So your exponential equations would look like this. You'd have 1.0 something usually in here, right? If you were talking about decay, if it was decaying at 3%, you would take 100% minus 3%, and so you would get 97% in your equation like that. So that's the kind of equations we did before. In some situations, things grow continuously. They start growing and they don't stop, or they decay and they don't stop. And so we have to have a slightly different equation for those, because it's like continuous compounding, it's continuous growth and decay. And so you'll see the equations right here. The only difference is instead of the 1 point something to make it grow, or the 1 minus percentage to make it decay, we've got the number e, you got the natural number in here. But the structure is the same. You got y equals, like your current number equals your starting number times e to the power of kt. And k this time is where the rate goes in the exponent. And the only difference is growth has a positive exponent, decay has a negative exponent. So it's pretty easy to deal with. I think it's easier than having to add or subtract from 1. We just have to remember to make it grow, the exponent is positive. To make it decay or get smaller, the exponent is negative. It kind of makes sense to me. So let's run through a couple examples just to sort of make sense of this thing. So a common place that you'll see continuous decay is in radioactive isotopes, radioactive decay. So, with certain unstable elements, it loses its mass to subatomic particles over time. And so sodium-22 has a rate of continuous decay of 0.2666. Okay, and so this is our K value that's going to go in the exponent up here. And then it asks how many years will it take a 40-gram sample to lose half its mass. So we're kind of talking about half-life. Okay, so we just start plugging things in. Well, I guess first of all, we have to decide is it growth or decay. Okay, well, it tells us right here, it's got continuous decay. Okay, so I'm using this one with the negative exponent. And so y is the current amount that we have. Okay, and so I don't see it in the problem. I'm saying how many years will it take a 40-gram sample to lose half its mass? We have to think, okay, if I'm starting with 40 grams and I'm going to have half its mass remaining, then at some point I'm going to have 20 grams instead of 40. Okay, in this decay equation, A is still the starting amount, just like any other exponential function. So we put 40 there, and then always E to the power of kt, or negative kt because it's decay. So negative 0.2666, that was our K value, that's our rate of decay, times T. And so it says how many years, so we're looking for T. In this case, our variable's in the exponent, and that's kind of why it comes after the logarithm section in this unit. And so now we have an equation to solve. Okay, well, let's see. Let's divide 40 from both sides. Okay, so 20 divided by 40 is 0.5, and that's going to equal that E expression, like that. And so now we need to get rid of the E, or get this E out of here, get this T out of the exponent. And so one of the tricks we learned to do that was just to take the natural log of both sides. So if I take the natural log of the left, I get the natural log of 0.5. On the right, if I take the natural log of this exponential expression, natural log says what power of E makes E to this power? So essentially it just cancels the E off. So we get that exponent for that whole side of the equation. So natural log and E are inverse operations. They cancel each other out. So do the natural log of both sides. You get natural log of 0.5, and then so the E disappears over here. Then to solve this, all I have to do is divide by this decimal. So you take the natural log of 0.05 and divide it by this thing. And let me grab a calculator and see what that is. So natural log of 0.5 divided by negative 0.2666 is 2.5999, so about 2.6. And then that's for years, so 2.6 years to lose half its mass. Okay, next example, population growth. The population of China is currently 1.44 billion. In the year 2000, it was 1.28 billion. We wanted to determine a growth equation model. So that equation is still the same thing. We're still talking about continuous growth, right? The population is so big, it's almost like that it's growing continuously. So that growth equation was like that. Y equals A times e to the kt. And so we need to fill in what we know. Okay, in this case we know y. Y is the current value. The current population of China is 1.44. So that goes in for y. Oops, let me actually put it in an equation. 1.44, and then equals the starting value. So we're starting counting in 2000. So we'll use 1.8 billion for the starting amount. And then we got e to the kt. Now in this is not telling us the growth rate anywhere. So I gotta leave k as a variable. And then does it give us time? Well, kind of. It says the population of China is currently, in the year 2020, 1.44 billion. And in 2000 it was here. So kind of hiding in there, we have a time value of 20 years. And so now we have k as our variable, and we just need to solve for what that growth rate is so that we can make a model for China's population growth. And this solves the exact same way as the other one. So we start by dividing 1.44 by 1.28. And that's 1.125. So 1.125 equals e to the power of 20k. Just going to flip those around to make it look sort of normal. Right, so I just divided 1.28 on both sides. Got rid of it over here, and I got 1.125 over here. And now I'm at that point where I need to get the exponent off the e. And so that's natural log time when that happens. So we take the natural log of 1.125, and the natural log of e to the 20k is just 20k. And so then all I have to do is take the natural log of 1.125 and divide it by 20. Okay, that's calculator time. And that gives us 0.00589. So there's the growth rate for China's population, 0.00589. And so the question said determine a growth equation. So you don't want to stop here. In this one, we want to make sure that we answer the question accurately. It says write a growth equation. So the growth equation, we just take sort of the population value, the current population value out, and put the other stuff in, and take time back out. So we got y equals our starting value of 1.28, always e. Now we know the growth rate is 0.00589, and we'll put the t back in there like that. Okay, so we want an equation we can use to predict the population of China at a given time from the year 2000, and that's what we got. And then there's almost always a follow-up question asking you to use that equation that you made. So we want to say, when will China's population reach 2 billion people? Okay, so that's a lot. So let's use our equation and figure it out. Okay, so our equation is right here. Y equals 1.28 e to the power of 0.0589t, where y is the amount we're interested in. And so we're interested in 2 billion people. So that's going to go in for y, 2. Still got 1.28, still got e. K is k. I mean, we're assuming that the growth is going to stay the same. And then we don't know the time. That's what we're looking for. When's it going to happen? Okay, and so solving these exponential equations, once you can set it up, it's almost always the same. Take both sides and divide them by 1.28 to get rid of it over here. So 2 divided by 1.28 is 1.5625. And so that equals e to the power of that crazy decimal again, times t. Next step after you divide is to natural log both sides to get rid of the e. So this becomes natural log of 1.5625. And then on this side, the e goes away. Right? E and natural log cancel out. And so you just get your exponent back. Okay. And then the last step is to solve for t by dividing by this decimal. So take the natural log of this stuff divided by this stuff. Okay, so let's see what that is. Natural log of 1.56265 divided by 0.00589. Oops, I typed the ones. 0.00589 is 75. So it's 75.787, something like that. And so it says, when will China's population reach 2 billion? Well, it happens in 75 years after we started counting, about almost 76 years after we started counting. We started counting in the year 2000, so it should happen if growth stays the same in the year 2076. When you guys are like old and I'm dead. Yay. Okay, another common place that we'll see continuous growth is in continuously compounding interest. And so this is kind of a famous equation. A equals Pert, okay? And so it's the same structure, right? We still have our starting amount, we have E, and we have a rate, and we have a time. So it's the exact same equation. We just give it different variables when we're talking about finance. So A is the amount of money we have to have after T years. P is the principal. Remember, that's just a fancy way of saying your starting amount. And R is the interest rate. Okay, and so we can play around with this kind of stuff. So when Angelina was born, her grandparents deposited $5,000 into a college savings account that pays 4% interest compounded continuously. Okay? So assuming no withdrawals, how much will be in the account when Angela turns 18? So after 18 years, what's happening? So we just got to use A equals Pert and solve for what we know. Now in this case, we want to know how much money is in the account at a particular time. So that's what we're looking for is A. P in Pert is principal. That's your starting amount. So $5,000 is what she started with. Then you got E to the power of RT. And so R is the rate, 4% interest. Don't put 4 in. You always put the interest rate as a decimal. And then we are looking when she turns 18. And so at that point, you're just putting that in the calculator. So 5,000. Your E is a second LN on a TI-84 or TI calculator. Just second and then the LN button will get you an E. And then you got 0.04 times 18 in the exponent. And so that is $10,272 about. Okay, so over double the money in 18 years. Okay. Now we want to go the other way. We want to think about how long will it take the balance to reach $20,000. Okay, this time we have a dollar amount that we're interested in. We want to know when does it get to 20,000. Still starting at 5,000. Still always E. Still 4% growth. Now we don't know the time. So T is our variable in this one. And so this is just like the population one and the sodium 22 problem that we just did. We're going to take that $20,000 and we're going to divide it by 5,000. So that's 4 equals E to the power of 0.04t. Take the natural log of both sides to get rid of that E. Natural log of 4 equals 0.04t. That's a Y, that's a slash, that's a T, there we go. And then natural log of 4 divided by 0.04. And we get T is 34.7 years. So by the time Angelina's 34, she would have $20,000 if everything kind of stayed the same. Almost 35. All right, how much would her grandparents have to deposit if they want Angelina to have $25,000 in her account when she turns 18? Okay, so this kind of problem is asking how much should they set it up for Angelina to have that amount of money. So we're still doing A equals Pert. Okay, A this time is 25,000. Principal is what we want to know this time. We want to know how much money should we put in the account to make this happen. So P is our variable. We're still talking about that 4% account, and we're still talking about 18 years. We're back to talking about 18 years. And so now we solve this thing. Okay, well, you got to remember that E is a number. So this E to the 0.04 times 18 is a number. Okay, so we just need to use a calculator to figure out what that number is. Okay, so we got P times whatever that stuff is. So let's see. So E to the power of 0.04 times 18 is 2.0544. We'll leave some decimals in there. And so now to solve for P, we just need to divide 25,000 by that decimal. Divide by 2.0544. And so we get P equals 12,169. So $12,169, if they put that amount of money in this account, it will grow to $25,000 for when Angelina turns 18.